Good everyone. So everyone here is working on various ways to try and fix the internet. What's actually wrong with the internet? It's a pretty amazing creation of humanity. It's enabled us to create loads of all these amazing apps which have made people's lives better and simpler. But the way I see it, there are three major problems with the internet. The first is that it's fragile. And I'll get to exactly what I mean by that in a second. The second major problem is that the internet's constantly decaying, and we're losing at a fairly significant rate content that's on the internet. And the third problem is that it's slow. So now let me go into some more detail. I'd argue that the main reason that it's fragile is because of the centralized architecture that's evolved. So we've got a handful of websites, services which we all talk to, and they run on a handful of servers, and we all know what we mean by that. So, but what are the consequences of that? There's a single point of failure. Most of these services are designed such that you have to be online, and it makes various things like makes man-in-the-middle attacks a lot easier, makes distributed denial of service attacks easier, and this has real human consequences. So, for example, it means that your ISP or your government can turn off the internet, as happened in Egypt in 2011. So this is a real problem. So now the second problem, the decay. So there's about 5% link rot on the internet. So all your bookmarks, your favorite blogs or whatever, they're decaying at about 5% rate. So they'll end up being dangling pointers to nothing. If you're lucky. So the third problem, why is the internet slow? We have super fast local area networks. We have super fast internet backbone. But what connects the two? Molasses. And this is only going to get worse. So I've got speaking of slow, this is slow. Pretty sure I clicked there. Oh. Right, so there's this law called Nielsen's law, which basically says the bandwidth of a high-end user's internet connection gets faster at about 50% per year. And that's been pretty accurate for about 30 years. So if we assume that's going to continue on, there's the other trend is called Kreider's law, and that's that storage, and by storage I mean essentially the capacity of hard disks, gets larger at a rate of about 60% a year. So slightly faster rate. Say slightly, they're both exponential. But so what does this mean? After say 15 years, the size of disks has gotten 1,000 times bigger, but the bandwidth to the internet has only got 440 times bigger. So, and you combine this with Moore's law, and this means we end up with endpoints which are both very powerful and very big, but the connections between them are very weak. And if we look a little bit further into the future, what happens when we have a Mars base, or a moon base, or a Mars base? So the minimum latency by the speed of light to the moon is about a second. And to Mars, depending on the time of year, the minimum is about 4.5 minutes. So when we're in this kind of situation, apps have to work offline because you essentially are offline. So now, fact. Video traffic forms about 90% of IP traffic on the internet, according to Cisco. And there's a very good reason for this, coming back to centralized architecture. So someone watches a video on YouTube, they send a request to YouTube, and it bounces through about 10 servers on the way to YouTube. And then YouTube sends whatever it is, 100 meg video, back through those 10 nodes. And so if that's 100 meg video, you've just wasted 100 meg of bandwidth of each of these 10 links all the way up there. So now, for a second, imagine that I'm giving a lecture in a lecture theatre. And imagine that I give a link and I tell everyone to go and look at it. I'm not saying I'm doing that. Then everyone in the lecture goes and clicks on this link, and the first person will do exactly what I just said, go through the however many hops up to YouTube, download the video. Second person, same thing. So if we've got 30 people in the room, then you do the math, 100 meg video, whatever that is, 3 gigabytes of bandwidth all the way to YouTube and back. Now, clearly that's inefficient. It's the same file that everyone's getting. So there must be a better way. So IPFS hopes to solve these 3 problems that I've mentioned. And yeah, in that sense, be an upgrade for the web. So there's a bunch of goals. IPFS is distributed. It aims to be a permanent web. It's safer, for reasons which we'll get to. It's faster, smarter, and it forces you to write apps in an offline first mentality. There's a nice comparison. So IPFS is essentially trying to turn the internet into one big Git repository. And Git did to source control what IPFS is trying to do to the internet. So Git allowed you to work offline. You didn't have to be connected to your central repository, and you can still commit and share commits between you and this kind of thing, and it just works. So there's a similar idea with IPFS. So IPFS is an implementation, but it's also just a protocol. It's a hypermedia transport protocol for the web. So IPFS tries to combine the best ideas from a handful of technologies. So underlying it, there's a distributed hash table at the bottom. It uses BitTorrent to transfer fragments of files in a fast way. The data structure itself is the same as the one that's in Git. It has a self-certifying namespace for mutable data, which we'll talk about later. And on top of all that, you have the normal web. So this is a kind of protocol hierarchy for IPFS. So in the middle is the core data structure, which the whole thing is based on. And the whole thing is pluggable and customizable insofar as it's transport agnostic. You can use whatever transport you like. You can also change the routing in the DHT. You can use Tor if you want. There's the exchange for actually transferring the files. There's like BitTorrent, BitSwap. And then on top of that, so this is the Merkle DAG, that's the central data structure. On top of that, you have various naming schemes. It has its own interplanetary naming system. You can also use DNS, Namecoin. As I say, it's pluggable. And on top of that, you get applications which use it. So this is a quick look at the central data structure in Git. So it's called a Merkle tree or a Merkle DAG. Essentially, it's a graph, or it's a directed acyclic graph, where the links between nodes are content address links. So what I mean by a content address link is basically it's the hash of the file that you're asking for. And this leads to a lot of nice properties, which we will talk to. So let's take a step back and see how normal URL scheme works. So the very first part, you have the protocol. The second part is a location, whether it's a DNS name or an IP address. And the last part is the name or path of what you're actually asking for. So basically the location is a phone number, and that says, okay, I'm going to make a call to this particular machine, this server somewhere, wherever it is. And when I get to that call, when they pick up the phone, I'm going to ask them for this file. And they're going to reply with something. They can reply with whatever they want. And that's where the danger of the man in the middle actually lies. You don't actually know what you're, like you have a name, but you don't actually know what you're asking for. So the way this works in IPFS is, oh, that's not very readable. This says /IPFS.
That one is more bright.
Okay. Well, yeah. The blue part, the first part is IPFS, that's essentially the protocol. And then the second part is a hash. And so what that says is I'm asking the network for a file that has this hash. And the last part, we'll get to in a second, but that's to follow any links. So when I'm resolving this IPFS address, I basically say to the network, give me the thing that has this hash. And I can ask that of the machine next to me, of some random server online. It doesn't matter. As long as I get something, when I get it, I can check independently that I got what I asked for, because I just hash it, which is quick and easy. And if the hash is wrong, then it's the wrong thing. So this totally rules out being man in the middle. It's just not possible. And where these paths come in, objects in IPFS, as I'm saying, it's a tree that have links. And the links, so if we were to download this first object, it has a set of links to other objects, which are, again, just hashes, but they're named links. So what that means is I get this thing, and then go to the link that's called home, and then get that thing, and then go to the link that's called readme. So you end up with this immutable namespace. So yeah, I've mentioned it's distributed. Anyone can serve either file, man in the middle proof. Offline first, in the sense that Git is, you can commit locally, and it will just, next time you connect, it will end up on the network. And because it's immutable, it doesn't matter. There can be no clashes, and it's fast. Because of that, I can talk to the machine next to me, kind of thing. So, as I mentioned, Git, the core data structure in Git is a Merkle tree. IPFS is like a collection of these Merkle trees, and we transfer them with BitTorrent to make it fast. Bitcoin itself is also a Merkle tree, so one could trivially build Bitcoin on top of IPFS. And yeah, IPFS is a forest of Merkle trees, if you like. So the IPFS project, we're looking for help. You can find us on GitHub under IPFS. There's a Freenode channel. It's currently being organized by a company called Protocol Labs, which is a YC-funded company. But it's all done in the open. It's all open spec and open source. So I can talk more about some of the details, but that's the end of the slide part of the talk. Maybe the first thing I'll say is about, I've described how we get immutable data. How do we get mutable data? So that comes under the naming scheme. And fundamentally, you just need a way of transferring, looking up from a name to a hash in IPFS. And there are various ways to do that. The built-in way in IPFS, called IPNS, is essentially you have a key pair which you've generated from somewhere. You publish the public key, and it ends up into IPFS itself, and it ends up under the hash of the key. So it doesn't matter what encryption scheme you're using. And then the layer, the IPNS layer, lets you basically add a pointer to a particular IPFS hash under that key, obviously verified by the public key. You can also, they have a way of adding TXT records into DNS records, so you can use the DNS system as well, and you can see how it would work with other things like namecoin. So yeah, if there are any questions, then fire away.
What's next?
What's next? Well, so the way I've described it so far, there isn't any encryption. That's obviously an aim. This is aiming for speed, so it's you can layer encryption on top of this essentially, and that's what the applications will be doing. The IPNS, I mean, it uses cryptography obviously, but it's only signing. It's not encryption. So there's lots of things to do with that.
Where does the distributed nature come into it? Because you have the example with interplanetary, right, and late, so I guess like basically thinking one part is offline, so to speak. So I just really asked that maybe in a naive way, but BitTorrent, is it partitionable? Like, can you have different partitions that rejoin when you have BitTorrent?
Yeah, so certainly on the core IPFS level, because it's immutable, content addressed, you can just merge any if you had two separate IPFS networks, you can just merge them and there would be no clashes, simply because it's content addressed. If you go onto the naming level, because it's mutable, obviously there is a possibility for a clash there, but they have a pluggable validity scheme which you can use to determine how you merge those kind of records, and that's up to you basically.
What are your thoughts on sort of helping to bootstrap adoption?
Sorry, how to bootstrap?
Thoughts on bootstrapping adoption?
Adoption. Well, so there are already several people using it. It's the website NeoCities, which is like a new version of GeoCities, I guess. It's a web blog hosting platform. They're using it to archive their entire website base. There's also IPFS have just released. It's called Starship. It's an application using IPFS for deploying Docker containers. And so rather than, if you, for example, have a large container, rather than pushing it to all your deployment nodes, you only have to push it once and they send it between themselves, kind of thing. So basically it's just, building more applications with it, and people are definitely doing that.
I have two questions, they're probably the same question. What is the difference in doing exactly what you just said through BitTorrent and through IPFS? You say that if I have the hash of the file I want, I can just look for the hash on BitTorrent in the same way that I could look for the same hash on IPFS.
True, and so IPFS is just a protocol. It's an addressing scheme, so you can use whatever layers or transport layers that you want for it. And the BitTorrent side of it is just the transferring of individual blocks, parts of files, and how that's optimized.
The second question was, there was that slide, and can you explain how I can use, for example, a bit backpack? A bit, yes, exactly. So, can you explain how I can have something running on BitTorrent, something running on HTTP, and how can use IPFS together? So, in what situation would I use two different exchange protocols? Can you give me an example? If you have? So, is everyone hosting? It's the way you distribute data all through BitTorrent?
It's not BitTorrent itself. It's a BitTorrent-like protocol. So basically, the idea is everyone runs their own server of this, and those servers create a distributed hash table, which is used to both store and route these fragments around.
But if I run an HTTP server, how can that be distributed?
So what I'm saying here, this is an exchange mechanism for fragments within IPFS. There's also, there's a public gateway which is a HTTP server, gateway.ipfs.io, and that gives you a public gateway into IPFS itself. So it connects the normal web into the IPFS web. If you want, I can give you a quick demo of that. So let's see. I'm just going to add a file, which is IPFS add file name. Let's see. And this is a file that I haven't put in a network before. Well, as far as I'm aware, the network doesn't have it. So when I add a file to the network, I get back the resulting hash of that file. And so now, I'm just going to put the microphone for a moment. So now if I go to the public gateway, and put in the hash that I just got, so yeah, hopefully I'll get the picture. Now bear in mind I'm running this in a virtual machine on my laptop, and the virtual machine has its own NAT, which is protecting the virtual machines network, and then that has to go up. So I'm sending a web request. I'm sending a web request to their public gateway, which is wherever it is, and that has to go back down somehow and get into the VM on my virtual machine to find that file. So they've got obviously kinds of NAT traversal and this kind of stuff going on as well. If it will work.
When you add something to IPFS, what's happening behind?
Well, so when you add a file, you can fundamentally, if it's a large file, it will chunk it into smaller chunks, and each of those will end up as their own IPFS object. So you get deduplication on parts of a file as well, and then there'll be one sort of head which points to a list of them all, and that's the thing of the hash that we get back.
Are you telling to a tracker that I have that file?
So I tell that to I'm running a daemon locally in the VM, and that is connecting to the distributed hash table. So when I add the file, it basically announces I have this hash to the distributed hash table.
What about the replication of those chunks?
So if you're running an IPFS node, you can download any fragment you like. You can do what's called pinning, and that means your local node will always keep a copy of that particular hash. So that guarantees that will always be present on the network as long as you're present.
But do you need to explicitly sort of like get those chunks to propagate duplicates across the network, or does that happen automatically?
So that doesn't happen automatically yet. There's a sister protocol called Filecoin, which is essentially a storage-based cryptocurrency, and the idea of that is to incentivize other nodes to store fragments for you. So at the moment you store your fragments, and anyone else can get them. And then there's it's an independent layer.
Can I ask a question about file?
Sure. I know less about that, but I'll try.
Okay. So just it's very kind of just a high level question, right? So if I had a storage service that was optimized for lots of small files and a different storage service that was optimized for gigantic files, is there some easy way of routing requests to the better optimized service?
I think it's split in blocks.
So the large files are already split into fragments.
Okay.
I'm not sure the details of how they choose how to split those files. And that itself, that's how you choose to split the files, I know is pluggable, but I don't know the details of it.
But there's no notion that there's a kind of second-tier protocol for figuring out what storage backend you want to use. It's one storage backend that just handles lots of
It's one storage backend. I think there are works to, because at the moment they're just stored as basically files in a local database. There are moves to try and allow you to use some external storage provider, whether it's whatever it is, instead of the local disk. But yeah, that's a separate thing.
Does that section of the work have a name? Is there something I can look up online about that?
I've just heard it in discussions. So this demo is going brilliantly. Let me try another one. What I'll do is just create some file. Oh, oops, sorry. Right, so I just made a local file, let's add it. Right. Tried this half an hour ago and it just worked, so I'm not sure what's wrong now. Hang on. I have one theory, which is my. Yeah. Oh, it worked, so you could get there in the end. Very smooth in that, but yeah. So that's some public web server diving through various NATs into the virtual machine behind a virtual NAT on my laptop and getting the fragment and then serving it. So yeah, NATs are not fun.
One other question. So you said the fragments aren't encrypted when they're stored. So if you propagate some fragment into the network, you can put something illegal or revenge porn, control porn, something like that.
In the same way you can put something illegal on the web, yeah.
Yeah, but this thing is designed to be amorphous, right? In that content, so it's there.
It's always there as long as someone is essentially storing it and seeding it.
I'm not a cryptographic expert, so I'll just caveat that before you think I am. But I understand that the hash helps you authenticate a file because it's very difficult to make two files with the same hash. But in this instance, you're using the hash as a namespace, effectively.
Yes.
And it's mathematically quite possible for two files to have the same hash.
It's mathematically possible, but practically impossible if you choose a good hash.
It's a finite length string.
Yes, but if you look at the number of possibilities, there's more than the number of particles in the universe. So
Is it that big? Thank you very much for answering that question. Right?
It's even with birthday particles accounted for, unless you specifically work 94 algorithms.
Thank you.
Can you talk a little bit more about how IPFS works?
sure. So IPFS is key pair based. So you generate a key pair, you publish your public key into IPFS, and then at any point you can publish another hash from your public key. So essentially, it's a pointer from your public key to another hash, some other object in IPFS. And to update that, you just have to publish it again, publish a different one, which is obviously signed by your private key. So the network can verify that only you can update that, or only the holder of the private key can update that.
Is the purpose similar, I mean, from a user experience perspective, similar to DNS in terms of providing like human readable domain names that translate into hashes, or?
If you want a human readable stuff, so public key is just another hash. So as you can see, that's not very readable. So if you want something human readable, you can bootstrap DNS by putting a record into your DNS record with the hash essentially.
Okay.
And there's already a layer that sorts that out and looks it up for you.
And so what is the user, I mean, is there an intent for a user interface that doesn't rely on a gateway for like a web browser, or?
There is, there's already a web user, that's the wrong one. There's already a web user interface. If you're running the daemon locally, it's just a web interface. So this is the one for my current node. So you've got a peer ID, which is that is a public key of the node that is generated when it starts. And you can see that's the hash. Sorry, the public key is there. It has various network addresses which it can be accessed from. Actually, those are local ones. But yeah. And using the web UI, you can drag and drop files and do various things. See who you're connected to in principle. That's still a work in progress, but yeah.
So how would what would be the equivalent of a search engine for IPFS? Or is
So-
that necessary?
No, it's definitely necessary, and there are people working on that. Fundamentally, I guess they would listen for announcements of objects on IPFS and crawl them and just see what they are. Any other questions? What time is it? 8 minutes.
How are people storing blocks compensating for sharing?
So that's where the
Is there a file?
so for serving the files. So at the moment there's a BitTorrent-like protocol, so it's like tit for tat kind of thing. In the future there will be a Filecoin cryptocurrency-based version where you can incentivize people to store your fragments longer term. And that incorporates a proof of storage, proof of work, using again a Merkle tree, which is quite cool. But yeah.
Many Ethereum boys are extremely excited about IPFS, and I don't understand it very well, so I'd like to get that nowadays.
Yeah. Well, I mean, there's also two white papers. There's an IPFS white paper and a Filecoin white paper, which have most of the details in there, or at least for an overview. But yeah, you can find them on this website, I believe. Somewhere in there.
Is the intent that somebody will build a second daemon implementation?
Well, there already are two. So the core one is written in Go. There's another one written in Node.js, and they're aiming to make it hostable within a web page. So that would use WebRTC for the transport, and transparently talk to the rest of the network that way. Yeah, that's not quite working yet, but there's definitely a Node and a Go version at the moment. And there's API bindings in many languages, Python, Java, Scala, a few others. Because the daemon has a HTTP API, which is what the local web interface talks to. And yeah, there are already libraries binding to that API, so you can use it from other languages. All you have to do is run a daemon locally. Any other questions? Yep.
Someone already asked about is IPFS going to offer me to use readable names?
Not readable names, no.
Okay. But it's just going to offer me mutable.
It's a mutable layer on top of the immutable layer.
And I'm a question of mutable. When you mean mutable, means that you can change it, but you can always see how it was moved.
So given that the pointer to a file is a hash of the content of the file, if you change the file, you change the hash. So anyone who has that pointer will only ever find the original file.
The opposite's not true, right? If I have an IPNS hash, that hash never changes, right?
Correct.
Just
So
what the hash that it points to changes. Can I
Yeah.
find out what it pointed to before I updated the last time?
That depends on the implementation. Some want to keep the history, some don't. So IPNS currently, the simplest version of is this record valid is when you publish it, you sign it and you say this is alive for this amount of time to live, basically. But there's another one which is kind of like a blockchain where it's just a chain of hashed versions. So you would have a full history in that case, and it depends what the person wants to use.
But even if they use that, there's no way for me to evaluate that you didn't remove something from history. If you own the IPNS links, and you happen to choose to publish a day, a Merkle day, and then you decide later to rewrite history, I can't know it.
Correct. It's mutable, so you can do whatever you want with that.
So you can rewrite history.
If you control the namespace, i.e. the private key, yeah.
Is it possible to map? How do you envision mapping hashes to readable names?
So I mean, there's a system in DNS where you can put it, you can use that, or something like Namecoin or something like that. Any other questions?
Do you have any, for someone who just wants to dive in and experiment more, just recommend the website or any particular way to really just immerse ourselves in playing with it?
It depends on your background. If you come to one on command line, I'd say just install it and just play around with the command line interface. Otherwise, install it and there's a web interface you can drag and drop in. Or if you want to actually start writing programs to use it, then just grab one of the libraries which talks to it, and obviously install a daemon as well for it to talk to, and then play away.
I remember there was an interactive tool on.
You were demonstrating the web interface, I think, before. Is that what you're talking about?
No, I think there was an interactive tool or a tutorial, a video, which shows you how.
Yeah. So when you install it, there's a sort of getting started tutorial, and there's a tour, and there's various examples as well. So yeah, this is the install instructions, and then you've got getting started once you've installed it, and so on. So yeah, basically just dive into the website, IPFS.io.
So is there an intention that this will be deployed with a daemon on every node, or are those supposed to be separate?
I guess that is the intention, I believe.
You can, but if you don't want to be back to the network, you need to trust a node. So you can see the files from gateway.ipfs.io, but you have to trust gateway.ipfs.io to give you to serve your content. Which you can actually do by just checking the hash.
Exactly, yeah. If you wanted to, yeah. But it's a web server, so you could do anything.
Is there going to be a package like a desktop browser specifically with the daemon built in or something like that, or is
there are pre-built binaries which you can install, and the web interface is the web interface, or the command line if you prefer.
I'm just thinking from from a normal user's perspective, like someone who's maybe, I don't know, not going to actually be developing this, but just wants to use it to access content. I've already experienced in many networks that the IPFS gateway is blocked as for networks that like to block proxies.
All right, interesting. Okay.
So there's just one consideration in terms of.
Well, so once we have the in-browser version working, then if you can get somewhere to serve that up, then that would do it with a peer-to-peer
Right.
So.
How can you build an in-browser version? Isn't it fundamentally predicated on the daemon maintaining peer links all the time?
Sorry, maintaining
Links to peers all the time.
Well, it would use WebRTC to talk to and negotiate connections with other nodes.
So you're having a server on a web page, and as long as that page is open,
Yeah.
which doesn't really work.
People have done that. They've had websites hosted in a website.
It works if you're using it, but it doesn't work very well if you're serving from it.
Well, the main aim of that is just an easy way to someone to try it out and deploy it.
Okay, so it's not working.
Your browser, that page doesn't need to be connected to all the nodes. You just need to be connected to and log and nodes to be connected to the entire network.
No, it has to be connected to one node.
Yeah, it's one node. Yeah. Right, yeah. Right, thanks guys.